Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today we are going to discuss about the module Theory of Relativity-III from the paper Electromagnetic Theory. So from this modules you will get to know about the following. Firstly, you will understand the covariant form of the equations of electrodynamics, which provides the link between electrodynamics and the special theory of relativity. Then, we will discuss the electric and the magnetic field together as an antisymmetric 4-tensor of rank 2. After that, we will discuss the Maxwell's equations written clearly in a covariant form. Then, we'll talk about the transformation properties of the electric and the magnetic fields under Lorentz transformations. Then, we'll do the derivation of the field of a moving charge as an example of these transformations. Covariance of electrodynamics. We now discuss the covariance of the equations of electrodynamics. By this, we mean that the various equations governing the electromagnetic phenomena have the same form in all inertial frames of reference under Lorentz transformations. Remember, this is where the whole thing started. Lorentz and Poincaré had already shown, even before the advent of the Einstein's theory of relativity, that the equations of electrodynamics are not invariant under Galilean transformations. They are invariant under transformations which we now call the Lorentz transformations. In three-dimensional ordinary space, the invariance of the laws of physics is best demonstrated by writing them as relations between scalars, vectors, and tensors, etc. Though it is by no means necessary to do so. In a similar manner, the invariance of the laws of electrodynamics under Lorentz transformation is best demonstrated by writing them as relations between quantities having definite transformation properties under these transformations, that is, as relations between 4 scalars, 4 vectors, or 4 tensors, etc. This is what we mean by covariance. We know that the equations of electrodynamics are invariant. However, it is fruitful to put them in an explicitly covariant form. The volume element in the 4-dimensional space transforms as d4x prime is equal to dx prime superscript 0, dx prime superscript 1, dx prime superscript 2, and dx prime superscript 3, and this is equal to the mod of j times dx superscript 0 times dx superscript 1 times dx superscript 2 times dx superscript 3, and this is equal to the mod of j times d4x, where the mod of j is the Jacobian of the Lorentz transformation matrix. Covariance of electrodynamics. Now, the special Lorentz transformation that we have been considering, when the relative velocity of the two inertial frames is along the x-axis, then the Lorentz transformation matrix is given by lambda, which is a 4 cross 4 matrix, and the elements of this matrix are as follows. So lambda is equal to, the first row elements are given by gamma minus beta times gamma 0 0. The second row elements are given by minus beta times gamma gamma 0 0. The third row elements are given by 0 0 1 0, and the fourth row elements are given by 0 0 0 1. Now for this Lorentz transformation matrix, the Jacobian, that is modulus J, is equal to 1, and this is also true for any general Lorentz transformation that we may consider. Now since we already know that charge is invariant under any kind of transformation from one frame of reference to the other frame of reference, therefore we can write down the charge in terms of the charge density as dq is equal to rho times dx superscript 1 times dx superscript 2 times dx superscript 3. And from this relation, one can see that the charge density transforms as the time component of a 4 vector. So in this case, we can propose a 4 vector which consists of the charge density rho and the current density vector j. So the 4 vector corresponding to the charge density and the current density vector can then be combined together to give the equation of continuity, because we know that in the equation of continuity we have the equation in terms of the charge density and the current density given as the divergence of the current density plus the partial time derivative of the charge density is equal to 0. That is, del dot vector j plus del rho by del t is equal to 0. So this equation of continuity in the tensorial notation using the 4 vector charge current density can be written as, in the covariant form, del subscript alpha j superscript alpha is equal to 0. From this one sees the legitimacy of the charge current density 4 vector, that is of j superscript alpha as a 4 vector, and one also sees that this follows from the invariance of charge. That is, that the charge remains constant irrespective of the frame of reference in which it is being measured. So the Lorentz gauge condition using these above equations can be then written as 1 by c square del phi plus del dot vector a is equal to 0. Or we can write this as, that is, the Lorentz gauge condition can be written as 1 by c square plus del phi by del t plus divergence of the vector potential A is equal to 0. And using the Lorentz gauge, the equation satisfied by the potentials are then written as the Laplacian operator acting on the scalar potential phi is equal to 1 upon c times epsilon naught times whole times c times the charge density rho, and the Laplacian operator acting on the vector potential A is equal to mu naught times the current density vector j. The field-strength tensor. Now, after having written down the Lorentz gauge condition and having written down the equations of the scalar and the vector potential in the Lorentz gauge, which basically satisfy the wave equations, and also defining the equation of continuity in terms of the tensorial notation, it is now natural that we demand, or rather we look at the scalar and the vector potential also as a 4 vector quantity. So the 4 vector which represents the scalar and the vector potential is written as A superscript alpha is equal to phi by c and vector A, where phi is the scalar potential, c is the speed of light, and the vector A basically denotes or represents the vector potential. So using this 4 vector notation and the Lorentz gauge condition, we can then write down the equations in the Lorentz gauge as given by the Laplacian operator acting on A superscript alpha is equal to mu naught times J superscript alpha, while the Lorentz gauge condition takes the form del subscript alpha acting on A superscript alpha is equal to 0. And these are basically the covariant form of the Lorentz gauge condition and the wave equations in the Lorentz gauge. Now let us come on to the field strength tensor. This is where actually we need to very carefully understand that up till now whatever we have discussed, we could express those quantities in terms of the 4 vectors directly. So for example, we had the position coordinate 4 vector, we had the velocity 4 vector, and we had the energy momentum 4 vector, we had the charge and the current density 4 vector, then we had the scalar and the potential 4 vector. But now when we come on to the electric field and the magnetic field induction vector, then we have to see that whether these can be expressed as the 4 vector or not. And that is where we see that the way the Maxwell's equations are defined, we have to now introduce another tensor, which is called the field-strength tensor. So in order to understand how this field-strength tensor is going to represent the electric field and the magnetic field induction vector, let us first look at the last of the 2 Maxwell's equations, that is the Faraday's law of electromagnetic induction and the Ampere's circuital law. So looking at these 2 equations, we can then write down the electric field in terms of the scalar and the vector potential, and similarly we can also write down the magnetic field induction vector in terms of the scalar and the vector potential. So representing the electric field in terms of the scalar and the vector potential, we have the electric field vector E is equal to minus of the partial time derivative of the vector potential A minus the gradient of the scalar potential phi, that is minus del by del t of vector A minus del operator acting on phi, while the magnetic field induction vector is given as the curl of the vector potential A, that is del cross A. Now if we look at the components of these fields, then we see that the x component of the electric field is given by minus del A subscript x by del t minus del phi by del x, and writing this in the tensorial notation we get as equal to minus of del superscript 0 times c times A superscript 1 minus del superscript 1 times c times A superscript 0 bracket close. Similarly, the x component of the magnetic field induction vector is given by del A z by del y minus del A y by del z, where A z and A y represent the z and the y components of the vector potential, and this can then be written as in the tensorial notation minus of bracket open del superscript 2 times A superscript 3 minus del superscript 3 times A superscript 2 bracket close. Similarly, the y component of the electric field is given as in the tensorial notation minus of bracket open del superscript 0 acting on c times A superscript 2 minus del superscript 2 acting on c times A superscript 0 bracket close. The y component of the magnetic field induction vector is given by minus of bracket open del superscript 3 acting on A superscript 1 minus del superscript 1 acting on A superscript 3 bracket close, and the z component of the electric field is given by minus of bracket open del superscript 0 times acting on C times A superscript 1 minus del superscript 1 acting on C times A superscript 0 bracket close, and the z component of the magnetic field induction vector is given by minus of bracket open del superscript 1 acting on A superscript 2 minus del superscript 2 acting on A superscript 1 bracket close. So from these 3 equations representing the 3 components of the electric field vector and the remaining 3 equations representing the 3 components of the magnetic field vector, one can clearly say that the electric field and the magnetic field do not transform as components of 4 vector, but together as components of another antisymmetric second rank tensor. And the reason is clear, that since both the electric field and the magnetic field induction vector terms have the scalar potential as well as the vector potential dependence. So we can represent these 6 equations through an antisymmetric second rank tensor, which is called the field-strength tensor and is denoted by capital F superscript alpha beta is equal to del superscript alpha acting on A superscript beta minus del superscript beta acting on A superscript alpha, and this is equal to minus of F superscript beta alpha. So another important aspect that one needs to understand over here is that if we have an antisymmetric tensor, then if the indices are interchanged, then the sign of the value also changes. So if we have the second rank antisymmetric tensor F superscript alpha beta, then this will be equal to minus of F superscript beta alpha. The field strength tensor. Now we know that if we look at a second rank tensor, then in general a rank 2 tensor would have 16 independent components. When we consider a symmetric rank 2 tensor, where by definition a symmetric rank 2 tensor means that the rows and columns are interchangeable. That means if we interchange the index, then we must get the same value of the term. So in case of a symmetric rank 2 tensor, instead of 16 independent components, we have 10 independent components. While in case of an antisymmetric tensor, where by definition an antisymmetric tensor means that if the rows and columns of the matrix are interchanged, then the components undergo a change in sign only while the magnitude remains the same. So the diagonal elements of such an antisymmetric tensor are all 0. So in case of an antisymmetric tensor, there are only 6 independent components. So now again coming back to the field strength tensor, which is an antisymmetric rank 2 tensor. So the contravariant form of this field strength tensor is given as, it's a 4 cross 4 matrix where F superscript alpha beta is equal to, the first row of the matrix has components 0 minus E subscript 1 by C minus E subscript 2 by C minus E subscript 3 by C. The second row has components E subscript 1 by C, 0 minus B subscript 3 by C and B subscript 2. The third row components are E subscript 2 by C, B subscript 3, 0 and minus B subscript 1. While the fourth row has components E subscript 3 by C minus B subscript 2, B subscript 1 and 0. Now if we want to write down the covariant form of this field strength tensor, then using the transformation equation that we have discussed earlier, to go from the contravariant form to the covariant form using the metric tensor, we have F subscript alpha beta is equal to G subscript alpha gamma, F superscript gamma delta, G subscript delta beta. And using this transformation, we finally have F subscript alpha beta is equal to, the first row elements are 0, E subscript 1 by C, E subscript 2 by C, E subscript 3 by C. The second row elements are minus E subscript 1 by C, 0 minus B subscript 3, B subscript 2. The third row elements are minus E subscript 2 by C, B subscript 3, 0 minus B subscript 1. And the fourth row elements are minus E subscript 3 by C, minus B subscript 2, B subscript 1, 0. So it is, if you look the rank 2 tensors, that is the field strength tensors, in the covariant and the contravariant form, and you compare these two relations, then what you see is that the covariant and the contravariant forms of the field strength tensor differ only in the sign of the electric field terms. The magnetic field terms in these two forms remain unchanged, and thus we can then summarize this as vector E vector B goes to minus of vector E vector B when you go from the covariant form to the contravariant form, or vice versa. Maxwell's equations, dual field strength tensor. Now there is another way of defining the electric field and the magnetic field in terms of the tensorial notations. So one of the ways was that we had used the field strength tensor, and another way is to define the dual field strength tensor. So in order to define the electric field and the magnetic field in terms of this dual field strength tensor, we first define a totally antisymmetric tensor of rank 4, which is denoted by epsilon superscript alpha beta gamma delta, where this epsilon superscript alpha beta gamma delta takes the value 1 for alpha equal to 0, beta equal to 1, gamma equal to 2 and delta equal to 3, or any other even permutation of this combination or of these 4 terms. Epsilon superscript alpha beta gamma delta is equal to -1 for any of the odd permutation of the above symbols, and epsilon superscript alpha beta gamma delta is equal to 0 for any 2 or more symbols having the same value. So numerically we can write down epsilon superscript alpha beta gamma delta is equal to minus of epsilon subscript alpha beta gamma delta, and from this definition it also implies that it is a pseudo tensor. Now using this transformation and the field strength tensor, we can then define the dual field strength tensor, which is given as f small f superscript alpha beta is equal to half times epsilon superscript alpha beta gamma delta whole times capital F subscript gamma delta, where capital F subscript gamma delta is the field strength tensor and epsilon superscript alpha beta gamma delta is the antisymmetric rank 4 tensor defined above. So using this definition and this transformation equation, we have the dual field strength tensor small f superscript alpha beta is equal to, the first row elements are given by 0 minus of b subscript 1 minus of b subscript 2 minus of b subscript 3. The second row elements are given by b subscript 1 0 e subscript 3 by c minus e subscript 2 by c. Third row elements are given by b subscript 2 minus of e subscript 3 by c 0 e subscript 1 by c, and the fourth row elements are given by b subscript 3 e subscript 2 by c minus e subscript 1 by c 0. So if we compare this equation of the dual field strength tensor with the equation of the field strength tensor, then what we realize is that the elements of the dual field strength tensor can be obtained directly by doing a transformation of the field strength tensor by simply replacing the electric field with the magnetic field and the magnetic field with the negative of the electric field. Now let us come to the Maxwell's equation, so that after having defined the field strength tensor and the dual field strength tensor, which completely take into account the electric field and the magnetic field, we are now in a position to write down our Maxwell's equation in terms of either the field strength tensor or the dual field strength tensor. So the two inhomogeneous Maxwell's equations, that is the third and the fourth equation, which is the divergence of the electric field is equal to rho upon epsilon naught, which is the Ohm's law, and the curl of the magnetic field induction vector is equal to mu naught times bracket open current density vector J plus epsilon naught times the partial time derivative of the electric field bracket close. So these are the two inhomogeneous Maxwell's equation, and from these two equations we can then put them in a covariant form using the field strength tensor, and this is given as del subscript alpha acting on capital F superscript alpha beta is equal to mu naught times J superscript beta. Maxwell's equations. Now let us write down the two homogeneous Maxwell's equation also in the tensorial notation using the dual field strength tensor, and that can be written as del subscript alpha acting on small f superscript alpha beta is equal to 0. So in this way, using dual field strength tensor, we are able to express all the four Maxwell's equations where the two inhomogeneous Maxwell's equations are represented in terms of the field-strength tensor, and the two homogeneous Maxwell's equations are represented in terms of the dual field-strength tensor. So in the tensor form, we can then expand this to write del superscript alpha capital F superscript beta gamma plus del superscript beta acting on capital F superscript gamma alpha plus del superscript gamma acting on capital F superscript alpha beta is equal to 0. And from this, we can then finally write down the Lorentz force equation for a particle of charge q. So we know that the Lorentz force equation is given as the derivative of the momentum vector p with respect to time, that is the force, is equal to q, which is the charge, times bracket open the electric field vector, plus u cross b, which is where u is the velocity with which the charge is moving and b is the magnetic field induction vector. So this Lorentz force equation in the tensorial notation takes the form F superscript alpha is equal to d by d tau acting on p superscript alpha, where tau is the proper time and d by d tau represents the derivative of the quantity p superscript alpha with respect to the proper time, where p superscript alpha is the momentum for vector, and this is equal to m times d by d tau acting on u superscript alpha, and this is equal to m times a superscript alpha, and this can then be written as q times capital F superscript alpha beta times u subscript beta, where m is the rest mass of the charge, F superscript alpha beta is the field strength tensor. So using these definitions, we have now introduced the acceleration and the force for vectors, which are defined by the acceleration for vector a superscript alpha is equal to the proper time derivative d by d tau of u superscript alpha, and the force for vector f superscript alpha is equal to the proper time derivative, that is d by d tau acting on p superscript alpha, and this is equal to m times d by d tau acting on u superscript alpha is equal to m times a superscript alpha. From this above equation, the space components lead to the Lorentz force equation that we have just discussed above, while the time component, that is for alpha equal to 0, gives the equation d by d tau acting on p superscript 0 is equal to m times d by d tau acting on u superscript 0, and this is equal to m times gamma times d by dt acting on gamma times c, and this is equal to gamma by c times dw by dt, and this is equal to q times f capital F superscript 0 beta times u subscript beta, and this is equal to gamma times q by c whole times the electric field vector E dot product with the velocity vector u, and which is just the law of conservation of energy. Transformation property of the fields. Now let us discuss the transformation property of the electric and the magnetic fields. And we see that the transformation properties of the electric and the magnetic fields follow from the fact that they together form components of a rank 2 tensor. That is, that we can either define the electric and the magnetic field induction vectors in terms of the field strength tensor, which is an antisymmetric rank 2 tensor, or in terms of the dual field strength tensor, which is again an antisymmetric rank 2 tensor. So from these definitions, we can then define the transformation equations as f prime superscript alpha beta is equal to del x prime superscript alpha by del x superscript gamma times del x prime superscript beta by del x superscript delta whole times capital F superscript gamma delta, where capital F superscript gamma delta is the field strength tensor in one coordinate system or one frame of reference, while the F prime superscript alpha beta is the field strength tensor in the other inertial frame of reference. And this can then be written as in terms of the Lorentz transformation matrix, given as delta superscript alpha subscript gamma times capital F superscript gamma delta times delta superscript beta subscript delta is equal to, within brackets, the Lorentz transformation matrix delta times capital F times the transpose of the Lorentz transformation matrix delta whole superscript alpha beta, or we can write this as capital F prime is equal to Lorentz transformation matrix delta acting on capital F acting on the transpose of Lorentz transformation matrix delta, where capital F prime is the field strength tensor in one inertial frame of reference where the transformation is being sought, and capital F represents the field strength tensor in the inertial frame of reference from which the transformation is being made, where the Lorentz transformation matrix delta superscript alpha subscript beta is equal to del x prime superscript alpha by del x superscript beta. For the standard case of relative velocity in the x direction, that is when we are considering the relative motion between the two frames of reference only along the x-axis, the Lorentz transformation matrix is given by delta is equal to, the first row elements are gamma minus beta times gamma 0 0, second row elements are minus beta times gamma gamma 0 0, third row elements are 0 0 1 0, and the fourth row elements are 0 0 0 1. Multiplying the three matrices given above, that is this transformation matrix delta times the field strength tensor F times the transformation matrix transpose on the right hand side, and comparing term by term with the left hand side, we obtain the desired result. So we can then write down the final result as E prime subscript 1 is equal to E subscript 1, E prime subscript 2 is equal to gamma times bracket open E subscript 2 minus beta times C times B subscript 3 bracket close, E prime subscript 3 is equal to gamma times bracket open E subscript 3 plus beta times C times B subscript 2 bracket close. These three equations define the electric field transformation, where the symbol 1, 2 and 3 refer to the x, y and z component. Similarly, the transformation equations for the magnetic field are given as B prime subscript 1 is equal to B subscript 1, B prime subscript 2 is equal to gamma times bracket open B subscript 2 plus beta times E subscript 3 by C bracket close, and B prime subscript 3 is equal to gamma times bracket open B subscript 3 minus beta times E subscript 2 by C bracket close. Here we see that the inverse transformation for the above transformation equations can be obtained by a simple replacement of beta going to minus beta. So the inverse transformation equations are then given by E subscript 1 is equal to E prime subscript 1, E subscript 2 is equal to gamma times bracket open E prime subscript 2 plus beta times C times B prime subscript 3 bracket close, E subscript 3 is equal to gamma times bracket open E prime subscript 3 minus beta times C times B prime subscript 2 bracket close, B subscript 1 is equal to B prime subscript 1, B subscript 2 is equal to gamma times bracket open B prime subscript 2 minus beta times E subscript 3 by C bracket close, and B subscript 3 is equal to gamma times bracket open B prime subscript 3 plus beta times E prime subscript 2 by C. So these six equations define the inverse transformation for the electric and the magnetic field induction vectors. Transformation property of the fields. The general case. Now let us consider the case where we do not restrict the relative motion of one frame of reference with respect to the other frame of reference only along one particular axis. For example, up till now, whatever we have discussed, then we considered that the K prime frame of reference was moving along the x-axis with a speed v with respect to the K frame of reference. But now let us look at the general picture, that is, supposing if the K prime frame of reference is moving with a constant speed v in an arbitrary direction with respect to the K frame of reference, such that it is not aligned along any one particular axis direction. In such a case, the axes of the two frames are aligned, but the relative velocity v is along a general direction. So for this general case, the transformation equations of the coordinates, that is the Lorentz transformation equations, are given by t prime is equal to gamma times bracket open t minus vector beta dot vector x by c bracket close. Vector x prime is equal to vector x plus gamma minus 1 by beta square whole times within brackets the dot product of vector beta with vector x bracket close times vector beta minus gamma times vector beta times t by c. And hence the definition of the Lorentz transformation matrix also changes, and the Lorentz transformation matrix now, according to the relations of transformation of coordinates obtained above, is given as delta superscript alpha subscript beta is equal to del x prime superscript alpha by del x superscript beta, so that the delta, that is the Lorentz transformation matrix, is now equal to, the first row elements are given by gamma minus beta subscript 1 times gamma minus gamma times beta subscript 2 minus gamma times beta subscript 3. The second row elements are given by minus gamma times beta subscript 1 plus within brackets gamma minus 1 times beta subscript 1 square by beta square within brackets gamma minus 1 whole times beta subscript 1 beta subscript 2 by beta square within brackets gamma minus 1 times beta subscript 1 times beta subscript 3 by beta square. The third row elements are given by minus gamma times beta subscript 2 within brackets gamma minus 1 whole times beta subscript 1 beta subscript 2 by beta square 1 plus within brackets gamma minus 1 times beta subscript 2 square by beta square gamma minus 1 whole within brackets whole times beta subscript 2 times beta subscript 3 upon beta square. And the fourth row elements are given by minus gamma times beta subscript 3 within brackets gamma minus 1 times beta subscript 1 times beta subscript 3 by beta square within brackets gamma minus 1 times beta subscript 2 times beta subscript 3 by beta square 1 plus within brackets gamma minus 1 times beta subscript 3 whole square by beta square. And the transformation of the fields is then given by the relation. For the field strength tensor, we have capital F prime is equal to delta acting on capital F acting on the transpose of delta, and this leads to the electric field transformation equation given by vector E prime is equal to gamma times bracket open vector E plus C times cross product of beta with vector B bracket close minus gamma square upon gamma plus 1 whole times within bracket the dot product of vector beta with the electric field vector E whole times vector beta, while the magnetic field induction vector transformation equation is given by vector B prime is equal to gamma times bracket open vector B minus cross product of vector beta with the electric field vector E by C bracket close minus gamma square by gamma plus 1 whole times the dot product of the vector beta with the magnetic field induction vector B whole times vector beta. Transformation property of the fields. Now when we expand this equation in terms of the various components, that is the three components along the three axes, then in the component form these equations take the form E prime subscript 1 is equal to gamma times bracket open E subscript 1 plus within brackets beta subscript 2 times C times B subscript 3 minus beta subscript 3 times C times B subscript 2 bracket close minus gamma square by gamma plus 1 whole times within brackets beta subscript 1 times E subscript 1 plus beta subscript 2 times E subscript 2 plus beta subscript 3 times E subscript 3 bracket close times beta subscript 1 whole bracket close. E prime subscript 2 is equal to gamma times bracket open E subscript 2 plus within brackets beta subscript 3 times C times B subscript 1 minus beta subscript 1 times C times B subscript 3 bracket close, minus gamma square by gamma plus 1 within brackets, beta subscript 1 times E subscript 1 plus beta subscript 2 times E subscript 2 plus beta subscript 3 times E subscript 3 whole times beta subscript 2 whole bracket close. E prime subscript 3 is equal to gamma times whole bracket open E subscript 3 plus within brackets beta subscript 1 times C times B subscript 2 minus beta subscript 2 times C times B subscript 1 minus gamma square by gamma plus 1 within brackets beta subscript 1 times E subscript 1 plus beta subscript 2 times E subscript 2 plus beta subscript 3 times E subscript 3 whole times beta subscript 3 whole bracket close. Beta prime subscript 1 is equal to gamma whole bracket open B subscript 1 minus within brackets beta subscript 2 times E subscript 3 minus beta subscript 3 times E subscript 2 by C minus gamma square upon gamma plus 1 within brackets beta subscript 1 times B subscript 1 plus beta subscript 2 times B subscript 2 plus beta subscript 3 times B subscript 3 whole times beta subscript 1 whole bracket close. B prime subscript 2 is equal to gamma times whole bracket open B subscript 2 minus within brackets beta subscript 3 E subscript 1 minus beta subscript 1 E subscript 3 whole by C minus gamma square upon gamma plus 1 within brackets beta subscript 1 B subscript 1 plus beta subscript 2 B subscript 2 plus beta subscript 3 times B subscript 3 whole times beta subscript 2 whole bracket close. And B prime subscript 3 is equal to gamma whole bracket open B subscript 3 minus within brackets beta subscript 1 times E subscript 2 minus beta subscript 2 times E subscript 1 whole by C minus gamma square upon gamma plus 1 within brackets beta subscript 1 B subscript 1 plus beta subscript 2 times B subscript 2 plus beta subscript 3 times B subscript 3 whole times beta subscript 3 whole bracket close. So from these 6 transformation equations, we see that the electric field and the magnetic field do not have any independent existence. That is, in all these 6 equations, we see that the electric and the magnetic fields both are occurring. So even if the field is purely electric or magnetic in one frame of reference, it will definitely have components of both the fields in the other frame of reference. Also, the two are really integrated into a single object, that is the electromagnetic field. So from these 6 components that we have defined over here in the transformation equations, we can then say that given a tensor, we can form various scalars or invariants out of it. So in case of the field-strength tensor, the field-strength tensor has 2 independent ones that are given by F superscript alpha beta times capital F subscript alpha beta is equal to, or rather is proportional to, bracket open E square minus C square times B square bracket close, and capital F superscript alpha beta times small f subscript alpha beta is proportional to the vector E dot vector B, that is the scalar product of the electric field and the magnetic field induction vector. In particular, a purely electric field in one frame of reference cannot transform as a purely magnetic field in another frame of reference, where the 2 frames of reference are moving with respect to each other in a general direction. An example. Now let us consider an example in which we are considering the field of a uniformly moving charge. So if we look at the figure, let us consider 2 different coordinate systems or frames of reference. So in the K frame of reference, we have the coordinates x, y and z, while in the K prime frame of reference, we have the coordinates x prime, y prime and z prime. Now let us consider an example in which these transformations occur for a uniformly moving charge. That is how the fields will transform for a uniformly moving charge, which we commonly refer to as the Biot-Savart law. Further, let us consider that the K prime frame of reference is moving with respect to the K frame of reference, and that the charge Q is moving with a uniform velocity in the k frame of reference along the x direction or the x axis. Now let us consider that at some initial time t equal to 0, both the frames of reference are coincident, and further that their axes are oriented along the same direction. So let us now look at the coordinates of the observer and the charge in the two frames of reference. So in the k frame of reference, the location of the observer is 0, B, 0, and the location of the charge, if it is moving with a speed u along the x-axis, is after time t, u times t, 0, 0. While in the k prime frame of reference, that is moving with the charge, the location of the observer is minus u times t prime, b, 0, while the location of the charge is 0, 0, 0, because this k prime frame of reference is moving with the charge. The example continued. Now let us see that what is the distance between the charge and the observer in the k prime frame of reference. So in this frame of reference, this distance is given by r prime, and this is equal to under root of b square plus u times t prime whole square. And the field due to this charge in the k prime frame of reference is purely electrostatic, because the charge is stationary in the k prime frame of reference. Therefore, this field is given by vector E prime is equal to q times vector r prime upon 4 pi epsilon naught r prime cube, while in the k prime frame of reference, the magnetic field induction vector B prime is equal to 0, since the charge is stationary in this frame of reference. So we can write down the components of the electric field in the k prime frame of reference as E prime subscript 1 is equal to minus q times u times t prime upon 4 pi epsilon naught r prime cube. E prime subscript 2 is equal to q times u times t prime upon 4 pi epsilon naught r prime cube, and E prime subscript 3 is equal to 0, while B prime subscript 1 is equal to B prime subscript 2 is equal to B prime subscript 3 is equal to 0. In other words, the z component of the electric field in the k prime frame of reference and the x, y, and z component of the magnetic field induction vector in the k prime frame of reference are all 0. Now the transformation of time coordinates is given by t is equal to gamma times bracket open t prime plus u by c square whole times x prime subscript 1 bracket close, and this is equal to gamma times bracket open t prime minus u square by c square times t prime bracket close, and this is equal to t prime by gamma. So we can rewrite the components of the electric field in the k prime frame of reference as E prime subscript 1 is equal to minus 1 upon 4 pi epsilon naught whole times q times gamma times u times t time upon bracket open b square plus within brackets gamma times u times t times whole square whole bracket close to the power 3 by 2, and E prime subscript 2 is equal to 1 upon 4 pi epsilon naught times q times b upon bracket open b square plus within brackets gamma times u times t times whole bracket close to the power 3 by 2. Now once we've got these equations, that is the field equations in the k prime frame of reference, we can find out the field equations in the k frame of reference by using the transformation equations. So in the k frame of reference, we get the equations E1 is equal to E prime subscript 1 is equal to minus 1 upon 4 pi epsilon naught whole times q times gamma times u times t times by bracket open b square plus within brackets gamma times u times t bracket close whole to the power 3 by 2. E subscript 2 is equal to gamma times E prime subscript 2 is equal to 1 upon 4 pi epsilon naught times gamma times q times b upon bracket open b square plus gamma times u times t whole square whole bracket close to the power 3 by 2. B subscript 3 is equal to gamma times beta times e prime subscript 2 by c, and this is equal to 1 upon 4 pi epsilon naught c whole times gamma times q times b times beta upon bracket open b square plus within brackets gamma times u times t times whole square whole bracket close to the power 3 by 2, and this is equal to beta times e subscript 2 by c. All the other components turn out to be 0. So the electric field is in the x and y plane, and there is a magnetic field which is normal to the electric field, and this is as expected. So while in the k prime frame of reference we only have a purely electrostatic field due to the moving charge, and the vector E dot product with vector B is equal to 0, hence it is 0 in all frames. Further, in the k prime frame, the quantity E square minus B square, that is the square of the electric field minus the square of the magnetic field induction vector, is greater than 0. Hence, the quantity E square minus B square greater than 0 is true for. So students, now let us summarize what all we have learnt in this module. So in this module, firstly, we studied about the special theory of relativity and particularly the covariant forms of the equations of electrodynamics. Then we also discussed the covariance of the equations and provided the necessary link between electrodynamics and the special theory of relativity. Then we showed how the electric and the magnetic field together form an antisymmetric tensor of rank 2. Then we studied the Maxwell's equations and we wrote them down in an explicitly covariant form. And from there, we then worked on the electromagnetic field tensor and the transformation properties of electric and magnetic fields under Lorentz transformations. And we derived the same. Then we demonstrated clearly that the electric and the magnetic fields are to be regarded as one single entity. And we showed that the only way to account for the expressions of the electric and the magnetic field was to consider them as a single rank 2 tensor. Then we also showed that the field of a moving charge was derived as an example of these transformations. Thank you.